Let's look at the energy changes involved in forming a solution. So we can think about solution formation as happening in 3 steps. So the first step is here we have the solute, what we're dissolving, like the table salt. And in order for this to dissolve, we have to separate the pieces from each other, right? If they're held together very strongly, then the amount of energy needed to do that is going to be large. If they're not held together very strongly, it'll be small. But this will involve us putting energy in to the substance to pull those things apart, right? The next step we can think about is, well, what's going on with the solvent? We have to separate the solvent particles also to make room for the solute particles to get in. And again, here we're disturbing the attractive forces between those particles. So this is also going to be endothermic. We have to put energy into it. This is not just going to happen. So delta H for the solvent is also a positive number. And then we're going to look at the mixing of these two things. So we've separated the solute particles, we've separated the solvent particles, so now they're able to mix together, and now we'll be having some attraction between the solute particles and the solvent particles. So this is going to be a negative number. This is going to release energy. It's the enthalpy change for mixing. Because we had broken all those intermolecular forces, and now we're allowing some new ones to form. So this is going to release energy. The question is, how big are each of those? Right? So overall, the energy change for forming the solution is going to depend on how big those individual terms are. So forming a solution can be exothermic or endothermic. Here's one of those Born-Haber type things, which I know you guys love so much. So what we're looking at here is the solvent and the solute. Here they're aggregated, so they're stuck to each other. They're like in their regular form. And so in order to form this solution, we're going to have to separate the solute particles, so that's going to require an input of energy, and separate the solvent particles, that's going to require another input of energy. And now when we allow them to mix, that's going to release energy. The question is this release of energy larger than the sum of what we had to put in? If it is, then we've got an exothermic process. This is going to release energy. And so this is something where you mix them together and the solution might get warm. Over here, the mixing, the energy released by the mixing is less than the energy needed to separate the individual particles. And so here, this is an endothermic process. This is going to take energy in. So this is a sort of reaction or solution that they use for those instant ice packs, right? Where when you mix these two things, it forms a solution, but it's endothermic and it absorbs heat from the surroundings, making your sprained ankle get colder. Right? Any questions? So we're mostly looking at aqueous solutions of ionic compounds. And so what we can do here is we can combine that delta H solvent, so that's separating the water molecules, and delta H of the mixing the ions in with this separated solvent particles. We can call that the heat of hydration. So that's the enthalpy change that happens when 1 mole of gaseous solute ions dissolves in water. That is always going to be negative, exothermic, because we've got these ion dipole forces that are much stronger than the hydrogen bonding of the individual water molecules. So the heat of solution is the heat of separating the solute molecules, separating the solvent particles, and mixing them together. So this term together is always going to be negative for ionic compounds because we're making ion dipole forces and we're breaking hydrogen bonds, and this one's bigger. So the heat of solution is going to equal the heat of the solute, that's always going to be endothermic, plus this heat of hydration. We talked about the lattice energy of ionic compounds. And that's when you have the separated ions in the gas state and you allow them to come together and they form all those ionic bonds and it releases a lot of energy. The heat of solute for ionic compounds, the energy required to separate those particles into ions in the gas state is the same amount of energy as the lattice energy, it's just opposite in sign. So if that heat of solute is smaller than the heat of hydration, the solution process will be exothermic. The solution will become warm. If the heat of solute is greater than the heat of hydration, then the process will be endothermic and the solution will feel cold.